Alrighty. Good evening, everyone. We'll be getting started with a talk on heap exploitation in just a minute. Thanks for dropping by on a Saturday. Got rescheduled a bit, but back on track now. Okay, let's get going here. So, as a preface, we have a couple code examples on the website for you today. So, if you go to tools.rpis.ec, you'll be able to grab the examples as well as have a look at these slides we're presenting right now. But feel free just to follow along because we'll be going into them on stream. So we've seen a decent bit of stuff messing around with the stack, clobbering function pointers and generally messing around with other values on it, typically via, running over a buffer and corrupting memory. But what about the data that's not on the stack? And the first thing that might come to mind is, well, why don't we put everything on the stack? Because, stack's pretty convenient. It cleans up for you when you, return. It's all kind of just right there. It's pretty handy. The problem is that it's not really suitable for two kinds of things. Large blobs of data can be problematic because there's only so much space on the stack. That if you recurse a few million times, you generally blow up the stack and it crashes. Well, recursing a few million times isn't that much data. And so if you try to put a 5 GB blob in there, it's not going to fit. It's also pretty unsuitable for anything of variable size because that makes the math for moving the stack pointer around and actually accessing everything quite difficult. So in fact, in general, like the stack only contains a fixed size allocation. If you make an integer local to go on there, but if you just dynamically allocate some data, it's not going to be on there. So if it's on the stack, it's got to be somewhere else. And that somewhere else in this case is the heap. So the heap is a collection of dynamically allocated memory, which means that unlike statically allocated memory, we don't know ahead of time exactly what's going to be done. So it's acquired and released as the program runs, and the pointers you get to it are not they're not necessarily deterministic. They could vary from execution to execution, depending on where the heap winds up and how the heap is being used up to that point. And importantly, the heap is also global in that heap data isn't tied to a stack frame. When you return from a function, the stack frame for that function is popped, and the values in there are dead. They still exist, but they're no longer live. They'll get clobbered pretty soon, and you can't access them outside the function. So for all intents and purposes, they're gone. Conversely, heap data stays there, and it can stay there a little too long. It's quite easy to leak memory in the heap. When people talk about memory leaks, they're basically always talking about something allocates some stuff on the heap and then it never lets go. And even if you do keep that nice and clean, you can get lots of weird action at a distance with heap data because it's global. So you can have bugs that affect weird parts of your program you didn't even expect. And the pointers involved here can be corrupted, obviously. But more interestingly, they could also be rigged from the start. When the heap allocator gets messed up, interesting things happen. So obviously, putting stuff in the heap is useful. It's a good thing. But it does open avenues for a lot of new and exciting bugs. So libc, or I should say glibc, offers two functions that let you work with a heap. So malik, or memory allocate, acquires memory, and free will release it. And from a point of view, libc, it's magic. Malik will just, given a number, it just finds some memory. We don't know how. It just does it. It gives us the pointer. We use it. It's all magical. And even more interestingly, free doesn't need the size, and it doesn't need anything. It just needs a pointer. So What? How? How does it do this? Well, the answer is metadata. More specifically, chunk metadata. So, when you actually ask for a blob of memory with malloc, you get back a pointer into a struct. And that struct is the malloc chunk. So every time you allocate memory, you're getting a chunk. And that chunk contains some important information. So, for example, the size of the previous chunk if it's free, and we'll get onto what previous means in a second, as well as its own size. And so there you go. That tells you how it actually knows what to do with the thing, and then it has these forward and back pointers. And these are used to actually manage the bins. Oh, sorry, to manage the chunks. And again, we'll touch on that in a second. So here we have just a little visual representation of what that looks like. And this is cribbed from the modern binary exploitation class back in 2015. So they're using 32-bit here, but same premises apply. So we have chunk sizes, and we have a couple flags in there, and then all of your data. And the interesting little tidbit here is that user data is in the exact same place those forward and back pointers are. And, sounds a little interesting. I don't know. Something might happen there. It would be a big shame if something happened there, for sure. So, pretty straightforward, though. It's not a really complicated struct here. Just a few pointers. So a couple interesting things here. So the chunk actually starts before your pointer. So you get a pointer that's actually on a 64-bit operating system. It's 16 bytes ahead of the start, I believe. Or was it 8 or 16? I'll check that. But it's going to be a few bytes offset ahead. And the pointers to the next and previous free chunks, which are used when that thing is free and it needs to keep track of all its chunks it's got access to, overlap with where your data goes. So, you can have, and then of course, any data past that point will just kind of stay there until something else overwrites it. And chunks are at least 8-byte aligned. So that's why we can use those lower 3 bits here for flags, because we don't need that much precision. And just as a quick reminder, the heap grows down from low memory, because we say that memory goes from low at the top to high at the bottom. And the stack grows up from high memory, so getting a lower memory address. It's a bit weird. But so one thing to keep in mind here is that when you see a pointer that's 6 digits, that's probably on the heap. When you see, OX7FFFFF, that's on the stack. And that'll become really important in just a few minutes here. So I alluded to bins earlier, and indeed bins are how we actually keep track of these chunks. Because if we want to give memory to the user, we need to be able to actually say, okay, I have 10 chunks of size 32 bytes. I have a few of these 8 billion byte chunks, whatever. And we need a way to track all of that. So a bin is a linked list of chunks. Oh, really, it's a list of chunks. You might have 10 fast bins and I think 63 small bins, something like that. You have a whole bunch of these bins. And so you got things like fast bins, which are a single size and very small. So 32 bytes, 64 bytes, 40 bytes. It's pretty discrete here. And it's like a stack. If you free a chunk, it will be the next chunk that you allocate. So if I free ABC, I will then allocate C, then B, A later. You have an unsorted bin, which is where the small and large chunks go when they're free. And these small and large bins themselves, are more organized, and they're like queues. They, the last one in is the first one, or the last one in is the last one out. So first in, first out. Now, the specifics of this do vary with your libc. For example, tcache pops up in 2.26, I believe, and it's thread local fast bins, basically. So each thread will have its own little list of chunks, and they preferentially use those before rating the fast bins. So when we ask for a chunk, when we try to do a malloc, glibc will check those bins. If they find something of the appropriate size, they use it. And it will use the first thing that looks appropriate. So you can get a chunk that's actually larger than you need. But if it cannot find anything, it splits off a bit from a top chunk, which is kind of at the edge. It's like it's at the wilderness. It's the last chunk before memory we don't own. And if that top chunk is too small, then it will ask for more memory with the sbrk function, SBRK, I believe, and that will expand our heap and make more room. So at first, it's just chopping bits off the chop chunk, but once we have some things that we freed, we can then use them again later. And that's the whole point of this, is to make this as fast as possible, because as you can imagine, a lot of things allocate memory. A lot of things, want to, read data or, just do work. So this is getting hammered constantly. So it needs all these, complicated little bins and all these things going on. It's, performance. So to recap, each chunk of memory, every time you malloc, it has some metadata on it. Chunks are kept in bins, which are linked lists, and allocations are made from those bins if at all possible. So there's a lot of state being tracked here, like a lot of linked lists. And the mind kind of wanders to then, well, that's a lot of room for corruption. And indeed, a lot of things can go wrong on the heap. So let's start by looking at a simple example with tiny chunks. And for the sake of this little demonstration, we're ignoring the T-cache here, because it is just like fast, not just like fast bins, but a very similar kind of behavior, just local to each thing. So if I just malloc 3 little chunks here, 10 bytes each, that's going to give me a chunk, and a chunk. And I could print these out to see the pointers. If I then free A, B, and C in sequence, and then allocate again, I'm going to get those original chunks back. So when I actually do the freeing, I get C, B, A. C is on top because it was freed last. And so if I allocate again, C comes out, B comes out, A comes out. And if we have a look at these addresses here, that's indeed what happens. So I allocated and got a point to the A0, then C0, then E0. And when I freed A, B, C in order, and then allocated A, B, and C again, I got E0, C0, A0. So this is predictable. Like this, and this is again for the sake of performance. It's not like it's going to randomly decide, oh, today I'm not going to do that. I'm going to go serve the end of the list. It's always going to pick the very first thing it finds that looks right. It just gives it to you. So this is interesting, and this behavior is going to come up again later, but I want something really broken. So I think one thing that kind of plagues kind of new CS students who are trying to write C and C++, especially probably in data structures, is the dreaded double free. So if we look at this here, we made a little modification. I didn't free C, I freed A again. So this is a problem. Our fast bin doesn't contain CBA anymore. It contains ABA. So it's got the same pointer twice. Now, if we actually just freed A twice in a row, it would notice. It does say, oh, wait, hang on. The head of the stack, the top of the stack is the same as this. And that's a bug, and it crashes. But if we just allocate something else in the middle, it's fine. So if we allocate 10 bytes, we're going to get that A pointer, then the B pointer, and then critically, we get the A pointer again. The memory allocator has gotten screwed up, and it just gave us 2 of the same pointer. At least in theory, that's what it would do if it weren't for that blasted T-cache. So T-cache actually has some extra bits of, some extra precautions. And what it winds up doing is it checks if it basically writes something to that chunk, and it checks if that's there, and if it is, it will give up and just give an error and crash. Very sad. So yeah, it's a bit of overhead, and it winds up protecting against some forms of double free. Now, we can fix that by doing some gross stuff, and we'll talk about why this is so gross later. But if I just write some garbage onto A and then free it again, everything's fine. Well, most things are fine. I think we just screwed up the linked list pretty badly, but at the least this will function. And so we bypass that check, and now when we allocate, we free A, free B, free A, and then allocate the A, B, and C again, we're going to get A0, C0, A0. Everything's good. Well, everything's bad, but in a good way. And actually, another trick is to just fill up the Tcache list, and then the fast bins don't do this. So if you look at doublefree.c in the example code, you'll see that. And actually, if we have a peek at that here, I'll just slide us over to the virtual machine. So yeah, as I described, doublefree.c just takes takes some chunks, and then we just get clever and allocate some chunks and cram the Tcache full of them. And then we free A, B, and A in sequence, and that winds up causing a double free. And we can actually observe this happening. So first, we're going to look at this happening as it should. Let me just compile. So GDB, or at least with the GEF extensions, I believe other plugins will do similar things for you, will actually allow you to inspect the heap, which is quite nice. So we're just going to go to main here. Let's run, and let's see what the heap looks like. Okay, nothing actually really going on here. Let's skip ahead a bit. Let's see, heap bins. So right now, our heap has nothing in Tcache, and all these fast bins, you see the size like ORX 20, 30, 40, 50, 60, etc. They're all empty. Nothing, all the bins are empty. Clean slate. So let's start freeing stuff. You see that we allocated A, B, and we opened the non-broken one. We free A, B, and C in sequence, and then allocate them. So let's skip ahead. Free A. Look at our bins, and now we see we have this one thing here on Tcache bins, and that's A0. And let's just step ahead again. Repeat the freeze a bit. Now we got two of them in there. You see this is a stack, so it's filling up, and then it's going to empty out from the same side. So we have E0, C0, A0. And as I step ahead in the mallocs, we empty out the Tcache. So yeah, and now it's empty again. We have reused all three of our, and if we run this program, you'll see that, yeah, we get A0, C0, E0, E0, C0, A0. Everything's okay. But now, let's look at the broken one. So, double free. Break on main, run that. We'll just step ahead a little bit. Actually, we're going to step ahead even further because I don't want to go through this whole loop. Let's go right to where we do the freeing. Let's see, break on 27. Continue. Okay, so here's our bins. As you can see, we've jammed up the Tcache bins up here with these kind of pointless chunks, so let's ignore those. And as I do the freeing here, I get a chunk, I get another chunk, and then here's the kicker. There's a loop. The heap inspector actually notices this. Like, oh, A0, C0, A0. That's no good. So this is, we have gotten the same chunk on here twice, and that's a problem. And as this continues, then it will print out A0, C0, A0. So yeah, the heap inspector is very helpful for when you're trying to get your head around what exactly is going on, because it can be quite opaque, especially if you aren't aware of Tcache, like I wasn't as I was putting this together. So yeah, let's come back to the slides. So that was a double free, freeing a chunk that was already free. So the allocator thought it had 3 chunks to work with, but it really only had 2, and 2 mallocs produced the same pointer. So this leads to a lot of problems. Best case scenario, you've probably screwed up the linked. You might have screwed up the linked list of chunks. If that happens, you'll probably just crash shortly after. But you can also get very weird breakage at a distance. Like, let's say that one of those pointers is to some user input, and one of those pointers is supposed to be to a struct with function pointers in it. So that's a big problem. So we wind up being able to write to one pointer and seemingly affect a totally unrelated thing. They're the same pointer, but that wasn't supposed to happen. So the double free, big problem, winds up opening the doors to other exploits down the road. So even if we don't double free, there's nothing stopping us from having two pointers to the same thing. So as I mentioned before, if we free A, B, and C, the next three mallocs of the appropriate size will get C, B, and A. So after a pointer gets freed, there's a good chance it's going to come back to life pretty soon. But now it's a stale pointer or a dangling pointer. It is a pointer to memory that we should no longer be touching because we said, hey, you let libc, I'm done with this, free it. But we still know where it is. And even if libc then hands it to someone else, we still see it. And this leads to use after free. So a use after free will allow us to mess with some remote, thing, whoever happens to get that chunk later on. And this can lead to the program exploding, or can lead to actual exploitation. So both use after free and double freeing will produce sort of similar behaviors. They both result in aliasing, where two different pointers go to the same place. Now, they aren't exactly the same. Like, chunks can actually get coalesced, they kind of get glued together. So, a stale pointer could wind up in the middle of a chunk or something like that. But they are conceptually kind of similar. So, as an example, suppose I had these two structs here. I had one that contains 16 bytes of data, and one that contains a function pointer. Well, if I write to that stale struct, I write to a pointer to that struct, after we free it, it might wind up smashing something else. We take control of a function pointer, bad stuff happens. So use after frees are pretty fun. We're kind of playing by the rules here. And that can make it, a little bit difficult to even find them in the first place. So let's just have a quick look at what a UAF might look like in practice. So here's a beautiful little program. It's just, it has those structs, or really just one struct in this case. I just malloc some data. So we malloc the data, we immediately free it, we allocate a struct, and in the real world, this might happen later, so maybe this is a buggy thing that, buggy network handler, and then later on, some important code happens to malloc and receive that chunk. Well, then that will allow us to, if we can still somehow write to that, that pointer. So maybe there's there's like something runs on a timer and it accidentally tries to update some data after it's freed. Well, suddenly we can actually, modify stuff at a distance. So let's just run this. So you see that we said, okay, this foo struct here, let's just set its foo attribute to be the lose function. And if we call that, indeed, we print out, okay, everything's fine. But then we just say, okay, well, star whatever equals win. And we would, naively not expect this to have any effect on foo, because clearly these are two different variables. But the pointer's the same place. And thus, oh no, terrible stuff has happened. Everything is broken. So we can overflow buffers on the stack. So why don't we overflow buffers on the heap? And this is not only possible, but it's actually easier in some ways. Like on the stack, they got, canaries. So they detect, oh, you've overrun a buffer and, possibly clobbered the return pointer. We're going to put a stop to that. Program stops. On the heap, that's not really a thing. Now, the heap layout can be unpredictable. because again, it's a massive sequence of allocations and deallocations, and these could occur in orders that are either difficult to predict or just kind of non-deterministic in general. The most obvious example being like a program might have a random timer that causes it to do something, and that will kind of shuffle around the heap. It's going to allocate things, empty out some bins. It's going to free some things and fill up some bins. So things can be complicated here, but sequential operations do often wind up in the same place, especially if you have kind of a fresh heap that doesn't have lots of scattered allocations that are currently live. So, really dumb example here. If f gets way too much data, it's actually possible to run over something and clobber another chunk entirely. So, just a real simple example here. This isn't anything too wild, really, but let's just try putting more garbage in. And okay, so foo here is couple bytes before bar. And if I have a look here, they're allocated together. So if I just put in a whole bunch of data here, the old key smash, indeed, foo will just overrun and smash into bar and clobber it. And again, this is not on the stack. The stack is totally fine. Like, no matter how much garbage I put in here, it's not, well, at some point it might crash. But the stack, it's not going to get smashed. Because this stuff is down at like OXB88. The stack is at like OX7 FFFF. It's way, way, way out there. So we're not hitting the stack, but we still can cause corruption. So just an example right here. A0, C0, and ONA. So once again, if we hit a function pointer, that's a little more fun. And actually, there's another example in the set, is just an actual, again, still very easy, but an actual exploit here. We call this Heap Overflow spicy. It's going to call this function pointer here, and then we just put a little garbage on there. Gets clobbered, program crashes. And if I run the little solver here, if I type it correctly, we can just, clobber a function pointer and take us somewhere else. Again, that's pretty basic. Nothing too crazy there. So one question that comes to mind is, like, how do we make this happen? Like, all these examples here, and the big example I have at the end, we had to write some code to do it. So in practice, we need to find a way to make the victim program misbehave to make it do what we want. So a heap exploit, might take us from a double free to something that actually gives us arbitrary, control of a function pointer. Especially if user input gets involved. So this is pretty complicated stuff, and it can wind up being a very elaborate exploit, especially once you mix in address space, layer randomization, and that kind of stuff. You have to find a way to leak pointers. And then given those leaks, figure out, okay, now I can go corrupt this thing on the heap and take us somewhere else. And just as more of an aside, because we're not going to get into these in too much detail today, but a whole bunch of heap strats or kind of exploits happen to be named House of X. We got House of Force, that was patched. House of Lore, House of Spirit, House of Orange, even House of Fun. I made that up, but it's actually real. But yeah, we're not going to get into those today because, one, they are significantly more complex, and two, a lot of them got fixed. glibc going from 2.23 to 2.31 patched up or added mitigations for a lot of these exploits. So that does make us wonder, though, hang on, why does this stuff work in the first place? Stack memory isn't in the heap arena. And so if I somehow tricked it into thinking the stack was a chunk, surely it should spot that. And if I put two copies of the same chunk in a list, it's obviously wrong. Surely it could just check the whole list, say, oh, you have a duplicate in there. Well, as I mentioned before, malik and free need to be ultra performant. They're used constantly everywhere by everything. And every single one of these checks adds overhead. You're doing more work. You're adding more cycles to that, that function. And there's actually a decent number of checks already. I grabbed this from a thing I'll link at the end, just a nice little ebook on heap exploitation. But it just lists a whole bunch of things that it does, like it checks is the do the next chunks actually the adjacent blocks actually refer back to me? Is my size correct? That kind of thing. So there are checks in here, and you have to evade things sometimes, but bad stuff happens nonetheless. And before we wrap up, I didn't get a chance to put this into the slides because I actually got this figured out pretty recently today. We're going to have a look at a kind of fun thing where we actually make a fake chunk. So remember that the chunk is just like a size, some pointers maybe. There's nothing really special about it. And so indeed, we can trick the allocator into thinking that things that aren't chunks are chunks. So let's have a quick look at this function here. So I've made a kind of a chunk here. This is all you really need to make a valid chunk, especially if we're doing fast bins where we don't have all those extra points at the bottom. We just have a size and some pointers. So I can actually say, okay, we're going to make ourselves on the stack. You see that this is just struct chunk. So this isn't like we're allocating something on the heap here. This is just stack. And we get a pointer to it and say, let's put some data. There's hello, just say hi. So what we're going to do then is, just like before, we're getting the T-cache out of the way. We're just filling that up so it doesn't interfere. Then we say, okay, we're going to malik a little chunk, immediately free it. But then we're going to say, okay, into that spot in memory, store a pointer to the evil chunk. And specifically, we store it to kind of the start point where the data would normally start in there. So evil chunk dot forward. And so this is actually going to point to that and say, okay, the next next free chunk is right here. I swear, honest. And so right now on the heap in the bins we have a single chunk, and we just messed with it. And so what we're actually going to do is then immediately allocate it. So now the allocator is going to look at it and say, oh, okay, the next chunk is on the stack. Okay. And from there, why don't we just have a look in GDB? So I'm going to fire up fake chunk. Let's break in main, give it a run. And let's just scroll down a bit. So we're going to go up to right before we start tampering. So let's break on line 46. Continue. Okay. So here's our heap. So let's see here. Where is my chunk? Step. Let's see. I'm missing my chunk. This is the demo gods punishing me for my hubris right now. Oh, there it is. I messed up my T-cache filling, but it still works actually. So let's run that again just so we can see what's going on. Okay. So when I write this, bogus pointer here, and you see this is actually showing us what happened. We're going to write into a pointer to the stack. And if you look at the heap bins now, suddenly the stack looks, or the bins look really weird. We got a chunk here, okay, that's all right. But then the next one has an address on the stack, and the size is kind of bogus too. And then after that, it points off into oblivion. There's nothing out there. It's totally bogus. So when I malik here, it pops the head off that stack, and now the next chunk it's ready to allocate is on the stack. So when I take a step here, that thing is gone, and it just, now we have a corrupted chunk, and I'm pretty sure I will get a crash if I try to malik again. And let's just continue. So the fake chunk on a stack starts at 80. And as we remember, there was 16 bytes of space, or OX10 space, for the size, previous size and the size. So when we malik this fake chunk, it gives us a pointer to the start of the data part of that struct. So it gives us a pointer to F90 here. And if we immediately read something out of that alleged heap allocation, we get hello. And I don't think that that that's not supposed to be there. And as we looked earlier, indeed we had written hello into this thing on the stack. So once again, we have aliasing happening, but this time we have a stack pointer and then another stack pointer that's supposed to be thing to the heap. So at this point, it's a lot like for it. I can, we say, okay, we'll put lose into that struct, but then we'll just write the win pointer into this thing, and this is supposed to be on the stack. This isn't a heap. It shouldn't be that. But indeed, when we call function pointer, we call win. So this is the premise. I believe this is a very similar to the premise of House of Force, which that one got fixed, at least got mitigated pretty recently, I think. 2019, something like that. This stuff is constantly in flux, which is both a burden and a boon, because it does mean there's new exciting stuff happening all the time. I'm pretty sure the original kind of Tcache implementation was even more vulnerable than everything was before. But it also means that you have to keep up with this stuff. It's constantly changing, and it can be a bit of a headache. Let's break out of that and just show it running by itself. So yeah, and here we see that F360. That's the actual, the chunk that we then brutally modified to trick the allocator. So yeah. So a lot of modern bugs involve the heap, and this even not even sort of modern, like going back to 2000, 2010, early 2010s. Oh god, that was 2010s, a decade ago now. They we're kind of moving away from really dumb, just overrun a buffer and run some shellcode. That stuff got fixed. And then we got stack canaries. So the stack is getting better and better to protect it. So the heap is really interesting, especially use out to freeze, because those lead to what we might call type confusion, where the program's kind of doing, thinks it's one thing in one place, but then it winds up being a different type somewhere else, and you wind up, getting control of the function pointer. So the heap is quite complex, and you can get things that might be benign in one circumstance suddenly blow up into, code execution in sudden circumstances. So there's a lot of good resources out there to learn. I made heavy use of these when preparing the presentation. Shellfish has a nice Git repo called How to Heap, and it contains a whole lot of examples. Some of them for modern libc, a lot of them for older libc. There's also a nice Heap Exploitation book by Double Copiel, aka Vampire, I believe. It's just nice little reference material. It talks about the internals. It talks about how the bins work, and it talks about a whole bunch of different kinds of attacks. So those are quite good to look at. And if you'd like to have a look at these things yourself, again, check tools.rpas.ec. We have both the slides and these demo materials on there. And you can give them a try. If you need a machine to run them in, we have the virtual machine. That's what I was using for the demos. Let's pull that up again for y'all. So we have all the examples on here, and you can see I have a lot of clutter from older ones. But yeah, so some nice stuff in there. And if you would like to connect with us, maybe ask some questions about, how on earth this heap thing working. Because even after figuring all this out, I still feel like I don't know where, even close to enough. You can join us on Slack at rpsec.slack.com. But with that, we're going to wrap things up. So thanks everyone for coming today, especially on this, bit of a delay today on Saturday. Next talk should be at the usual time, 7 p.m. Eastern on Friday. We hope to see you there, and we also hope to see you on the Slack. So thanks for coming.